Here's one more example using the integral test. And this time looking at the sum from 1 to infinity of n over e to the n squared. And I gave away the punchline there, but I am going to apply the integral test to this series. So if we're thinking about applying integral test, then we always need to first check is the function, which if I express this as a function of x, f of x equals x over e to the x squared, is that function positive, continuous, and decreasing? Okay, positive. So if x is 1 or larger, then the numerator is definitely positive. E, which is a positive number, raised to a power, will always be positive. So we have a positive over a positive, so yes, this will definitely be positive. Is it continuous? So it's continuous as long as this denominator is not 0, which if it's a power of e, then it's never going to be 0. So yes, it's continuous for all x greater than or equal to 1. Or this is actually continuous for all values of x. Is it decreasing? So this one, you can make an argument, a kind of subjective argument, just looking at this. But let's say we're really not sure, because I want to do this once in one of these example videos. So say you're looking at a function, you're not sure if it's increasing or decreasing, or you want to prove to yourself that it's decreasing. Then what you could do is take the derivative. Remember, the first derivative is what you use to figure out when a function is increasing, when is it decreasing. That's coming from the first derivative, think slope. So if we want to see that it's decreasing, we want to see that it has negative slope. So we want the derivative to be negative for all x from 1 to infinity. Okay, so let's verify that, just for the practice. So say we check the derivative. We'll have to use quotient rule here. So we take the bottom function, which is e to the x squared, times the derivative of the top, which is 1, minus the top function times the derivative of the bottom. So derivative of e to the x squared would be e to the x squared times the derivative of the inside. So times the derivative of the exponent there, which is 2x. Not equals 2x, but times 2x with the chain rule there. All over the denominator, e to the x squared, squared. Now remember, we just want to verify overall sign on this. So this denominator, e to the x squared squared, which in this case we multiply the exponent, so we could write this as e to the 2x squared if we want to. But I almost prefer it this way because it's more apparent that, it's more apparent that it's definitely positive because it's squared. But then again, it is also a power of a positive number, so we are pretty confident that this denominator is positive. So let's look at the numerator. Notice that I could factor out e to the x squared. I have a common factor of e to the x squared, so let me factor that out. Then what's left is 1 minus 2x times x, 2x squared. Keeping in mind that this is sum from 1 to infinity, we're thinking x is greater than or equal to 1. So this e to the x squared expression, this is definitely positive. But 1 minus 2x squared for x greater than or equal to 1, this right here will be negative for all of those values of x. And so overall, we have a positive times a negative in the numerator, so negative in the numerator over positive in the denominator. So this will be negative overall. So we can see now that the first derivative is negative for all values of x greater than or equal to 1. So yes, for sure, the function is decreasing. So there are times when you want to use integral test where the decreasing is not as obvious as it's been in these examples. This is what you could do. Take the first derivative, see if you can convince yourself that it's negative for all the values of x being considered here. So all of this to say that we're allowed to use the integral test. So now I want to actually use it. So get rid of this. It meets the criteria, which means that we can determine convergence or divergence of this series by considering whether the integral, or the improper integral from 1 to infinity of x over e to the x squared converges or diverges. Now, before I express this as a limit, let's go ahead and work on the integration. So if I'm integrating x over e to the x squared, try not to get carried away and apply integration by parts or anything fancy right off the bat. See if you can use a regular u substitution. So what if I write this as e to the negative x squared, so I'm going to bring this up, times x dx. And now, maybe you could see that if we let u equal the exponent here, if we let u equal negative x squared, then du, I'll use a different color, then du will be negative 2x dx. And we have x dx. So this is where you can do the thing where I like to do it where I multiply by negative 2 in here, so I squeeze in a negative 2, that multiple that I need, and then I multiply by the reciprocal negative 1/2 out here. If you like to solve for x dx or whatever, you should arrive at the same next step here. So negative 1/2 integral of e to the u times this whole, got too many markers, too many caps here. This whole negative 2x dx becomes du here. So it becomes just the integral of e to the u du. With a factor of negative 1/2 outside, which you guys might have found by dividing both sides of this equation by negative 2 if you prefer doing it that way. And then you also should agree that there's this negative 1/2 out here. And so the antiderivative then is negative 1/2 e to the u, which remember u is a stand-in for negative x squared plus c. And so I'll just clean it up. I'll put the, so negative exponent, I'm going to move it back to the denominator and make it positive again. So the antiderivative is negative 1 over 2 e to the x squared. So if I come back to this improper integral, then this is equal to the limit as t approaches infinity of this antiderivative evaluated from 1 to infinity. And the antiderivative is negative 1 over 2 e to the x squared. Evelyn, will you go ask them to be quiet when they come in? Will you ask them to be quiet when they come in? Sorry, I have kids that might come in and make noise. Okay, so just know that might happen. Oh, and this should be t now. Okay, so if we plug in limit as t approaches infinity, is this still visible? Of negative 1 over 2 e to the t squared minus negative 1 over 2 e to the first, then now as t approaches infinity, this limit right here has the form negative 1 over infinity. Denominator is increasing without bound. As t approaches infinity, e to the infinity, that's going to infinity. Negative 1 in the numerator, doesn't matter the negative here because it's just finite number over infinity. This is approaching 0 as t approaches infinity. And so this is 0 plus 1 over 2e. So 1 over 2e as our final answer for this improper integral. The improper integral converges to 1 over 2e. The actual value here, though, in these problems with the integral test doesn't matter at all because most likely the sum here converges to some other number. The reason for that is, in a sense, an integral does represent a sum, if you remember Riemann sums. But in that sum, we're letting x be any value from 1 to infinity, including, say, 1.5 and 3.6 and pi and all those numbers. X can take on any real number here. Whereas in this sum, we're only plugging in 1, 2, 3, 4, 5, 6, just the integers. And so, yeah, most likely these guys are going to converge to different numbers. But the important thing with the integral test is that because we got a number here, this improper integral converges to the number 1 over 2e, then this sum right here converges to something. It's a shortcoming of the integral test. It doesn't actually tell us what it converges to, but it does tell us for sure that this sum converges to some finite number.